let's, I guess we can get started. It looks like we have a couple folks online, and we have 1, 2, 3, about 10 people in person. So it's my honor to introduce Professor Rui Ni. He's coming here from Johns Hopkins University, where he's been assistant professor since 2018. Before that, he was the Kenneth K. Kuo Early Career Professor at Penn State. Ray received his PhD in the Department of Physics from the Chinese University of Hong Kong, and then was a postdoc at Yale. He's received an NSF Career Award, in Fluid Dynamics, ACF, PRF, Newer Investigator Award, and a NASA Early Stage Innovations Award. As you'll see, his background is in multi-phase flow. It spans both bubbly flow and gas solid. I think today's talk will be focused on bubbly flows. But I first met Ray shortly after I joined Michigan at a NSF review panel, and we quickly started chatting and realized we had research interests that overlapped, and then since then we've collaborated on a number of projects, and it's been real great fun. And Ray has some really unique experimental capabilities, and I'm very excited for this talk. So with that, I'll pass the mic, as they say. And I'll try to do my best to keep an eye on the chat. If anyone has a chat or a question, it might be easiest if you hold your questions to the end. But yeah, with that, take it away, Ray.
All right, just want to do a mic check. Can everybody hear me okay? I know you guys can.
Sounds good.
All right. Thank you. First of all, I really appreciate Jesse for having me here, and I know I'm the first speaker in person. It's a great honor to be here and sharing my research with everybody here. At the same time, I also want to say something about the COVID impact, and it's how pitiful it is to not be able to travel here and to share everything with you guys sort of before this time. And so this is actually a great opportunity for me to talk about a lot of things we're doing in the past 3 years. And hopefully we can make up for the lost time. I want to talk about the motivation here. So actually, there's something should be here, which is related to sort of COVID-19. But I'm mostly interested in a lot of the applications that relate to the air bubbles, oil pollution, ionization, and COVID-19 is another case where you have droplets sort of disintegrated smaller sizes. So in all those applications, we have this kind of important entity. This entity could be bubble, could be oil droplets, could be fuel droplets. And this entity could break down into a smaller sizes. And this is a very fundamental problem, not just in mechanical engineering, but could be also in chemical engineering. Actually, originally, it's a bunch of chemical engineers work on this problem because they were interested in oil emulsion and other kind of important chemical processes. But mechanical engineers started to take over this community because a lot of our processes, like for example, in University of Michigan, I would say the automobile and the fuel injection, the atomization problem is definitely intimately connected to this kind of fragmentation problem. So that's basically my focus today. I'm trying to say, what is this kind of fundamental mechanism behind this fragmentation of bubbles or droplets into smaller sizes? And in this problem, we typically assume the fragmentation is driven by some kind of a flow around this bubble or droplets. And this kind of flow has a typical velocity we call u. So today I'm not trying to give you very complicated equations with very complicated stories. I'm only have one simple story to tell you, which is about the Webb number. If you're trained as a fluid dynamicist, you've probably seen this dimensionless number before, and the Webb number is actually quite easy to understand. If you look at this equation here, you have two important contributing mechanism here. One is basically the rho u squared term. The rho u squared term is essentially talking about the pressure that's trying to drive the deformation and breakup of the droplets or bubbles. And there's in the denominator, you have the surface tension force, and that's basically relaxation that's trying to force the bubble or droplet to go back to spherical geometry. I mean, I hope that's clear to everybody today. So this dimensionless number, obviously, when it's larger than 1 or larger than a critical number, you can imagine that the bubble will undergo some kind of deformation, eventually break up, right? So that's basically the classical story about using the Webb number, saying the Webb number is sufficiently large, you have a breakup event, so you have a fragmentation. All right, so that's very clear. The next question you can ask is, what kind of U or D should we use in turbulence? So we had to pick a velocity scale for the surrounding flow to use, and we also had to pick a length scale for the surrounding flow to use. So what kind of a velocity scale and length scale we should pick? So to answer that question, we had to go all the way back to 1950s. Okay, so this is a time when a lot of exciting theories have been proposed as a way to deal with the fragmentation problem. So the classical framework is basically, again, treating the same kind of canonical problem. You have bubble or droplet, spherical geometry, and you throw that into turbulence. You can imagine it's immersed in an environment filled with a lot of eddies. Okay, eddies basically like the sort of elementary sort of flow structures. They are swirling flows, and they have a different kind of scales. So those are kind of the eddies we're talking about today. In those kind of problems, if you're familiar with the turbulence theory, if you're not, but that's okay. So there's a canonical theory about this, classical theory about this, which is energy cascade. So basically energy is stored in the large eddies, and they start to go, and as the large eddy break down into smaller and smaller eddies, so energy sort of cascade from large scale to small scale. It's like when you have a cup of coffee, you start to stir the coffee. In the very beginning, you inject the energy to the large eddy, but then the large eddy breaks down to a smaller eddy. So that's how you mix the coffee and cream together. When you look at the, if you rank those eddies from small size to large size, and then you measure their energy, so you find this kind of energy spectrum. In this particular problem, I call it structure functions. Basically, the smaller scale has a smaller energy, larger scale has larger energy. So this is basically the Kolmogorov 1941 theory. This is very well established, or the fundamental theory for turbulence. It's a very phenomenological, so there's no direct. So the derivation from Navier-Stokes equation is a part of that, but this is actually originally from the phenomena that Kolmogorov and Richardson observed. So in this problem, by the way, this 1941 theory is for single phase turbulence. There's no bubble in this problem yet. Okay, so in this problem, if you pick 2 points at a separation r, and you measure the velocity difference between the 2 points. So basically, you pick a point here, pick a point there. The separation between them is r. And if you quantify this so-called second order structure function, this is basically velocity difference to the power of 2. And you can write down this kind of power law relationship. C2 is a constant called Kolmogorov constant. Epsilon is energy dissipation rate. R is basically separation distance. And that follows this 2/3 power law. All right. So that's basically just for single phase turbulence. And later on in 1949 and 1955, this is actually two very famous work. We call it Kolmogorov-Hintz fundamental framework. So Kolmogorov did this in 1949, and Hintz extended that back in 1955. One of the key assumptions in Hintz's original manuscript, this is basically what I quoted from his work, is that, when we talk about Webb number, and they talk about the dynamic pressure that drive the deformation and the fragmentation of bubbles, the dynamic pressure, the most important dynamic pressure is actually caused by the diameter at the diameter of the droplets or the bubble in our case. So essentially what he said is, if I pick 2 points and get the structure function around the bubbles, I'm going to pick the distance to be the size of the bubble. That's basically the dominant energy source. If I do that, I can use this sort of an energy second order structure function, put that into the definition of Webb number. Essentially, I replace this U with this kind of a delta U squared. And you can see that this is basically assume that the dominant energy that drives the deformation and fragmentation is due to the eddy of the bubble size, because instead of writing R here, I wrote D here, and the D is basically the size of the eddy, the size of the bubble or the droplets. So that's basically the Webb number definition to use in turbulence. And there is a sort of an implicit hypothesis inside this framework is bubbles and drops are broken by eddies of similar sizes. And this is a very key hypothesis in the classical Kolmogorov-Hintz framework. And the Kolmogorov-Hintz framework has been used in many, many different applications, from the oil emulsion to the oceanic sort of wave breaking process and the bubbles entrainment in that process. So is this hypothesis correct? As an experimentalist, it's important to have a hypothesis that can be validated. So in that case, we need to actually design experiment to really test this hypothesis, because actually ever since 1950s, there has been no direct evidence to either prove or disapprove this kind of hypothesis. So let's check it. The first thing we want to do is we had to pick a system. I've been talking about bubbles and droplets as interchangeably before this slide, but from now I'm going to focus primarily on bubbles. And the two reasons: first of all, for bubbles, inner fluid has a negligible viscosity compared with the inner fluid has a negligible density and viscosity because that's air compared with outside fluid. So in that way, the surface tension is the only way that relax bubble back to sphere. If it's oil droplets, inner fluid also has a viscosity. So when you try to deform the drop, the viscosity of the inside fluid will also damp that motion. So that in that case, that's why we picked the bubble. Another reason is because of sponsors that use the bubble. So that's why we did it. That's probably more realistic reason here. So the Webb number, as I mentioned already, this is basically the Webb number in a classical Hopkins framework. There's one thing we have to keep in mind is, in addition to the turbulent stress that try to deform and break the bubble, for bubble, because of density difference, there's another source of energy that try to deform the bubble, which is due to the buoyancy. So there is this number called Armitage number, and it's a ratio between the buoyancy force that trying to, or the hydrostatic pressure, if you prefer, that trying to deform the bubble along the vertical direction to the surface tension. Essentially, the difference between these two numbers is one is deformed by the turbulent stresses, and the other one is deformed by the buoyancy. All right, so that's clear. And in order to test the Hopkins hypothesis, I need to make sure the Webb number is dominant. And the reason for that is because in the Hopkins framework, they didn't put anything about the buoyancy. But the buoyancy in experiment does exist. So I have to make sure the turbulent stresses or the bubbles are actually predominantly deformed by turbulent stresses instead of by buoyancy. In that case, I have to make sure the Webb number is larger than the Armitage number. If you write this equation in explicit form, then you have this kind of a turbulent stresses had to be larger than the buoyancy induced stress. And in order to satisfy this, we can actually calculate d and epsilon, because this is actually two parts of equations, and you only have two unknown. One is the diameter of the bubble, the other one is energy dissipation rate. So when I do the calculation, I realize that in order to satisfy this, my bubbles has to be a roughly order of a millimeter, and energy dissipation rate has to be larger than 0.5 meters squared per cubic second. If you don't satisfy this rule, if you go the energy dissipation rate smaller than this, the bubbles are always deformed by the buoyancy instead of by turbulence. So that's actually the first important takeaway message, is that we need to control the energy dissipation rate. And energy dissipation rate is basically a parameter in the turbulence that controls how strong the eddies are. So in this case, this is a very important parameter. Actually, this is a parameter that the experimentalists have been ignoring. And since the Reynolds number is the most important parameter people are trying to control in the turbulence community. I want to mention that this criteria is actually in oceanic environment is very easily satisfied, because for breaking wave in oceanic environment, energy dissipation could be as large as 12 meters squared per cubic second. It's definitely larger than 0.5. So in that case, a lot of bubbles entrained by the wave breaking can be easily fragmented by turbulence instead of by buoyancy. All right, so that's my sort of first message here. So I already mentioned that this is my question. Is a key hypothesis in the Hopkins framework correct? And in order to test this for bubbles, we need to have energy dissipation rate larger than 0.5. Here I wrote 0.1 because this is order of magnitude. We have to make sure at least we have to satisfy this kind of the criteria for energy dissipation rate. As an experimentalist, we checked a lot of different experimental facilities. One thing I want to emphasize that most of those facilities are for homogeneous isotropic turbulence. You can get a much, much higher energy dissipation rate if you're working on the turbulent jet or turbulent channel flow. Here, we only care about homogeneous isotropic turbulence. So that's why this is a facility I picked. And you can see that energy dissipation rate is not good enough for the application we want to do. Just to be fair, those works were not designed for bubble studies. They were designed for homogeneous isotropic turbulence, and they wanted to shoot for large Reynolds number. So for them, the energy dissipation rate was not the focus. So that's why they didn't get to very high. So this is basically the column I want you to focus on. All right, let's talk about the experimental facility we did. I spent several years of my life working on this facility. This is called the Vion set, and the name comes from all these things I put together. This is a vertical facility, which means the flow is actually coming vertically from top to bottom. It's an octagonal geometry, and the reason for that is because we want to have a lot of optical access to the interior of the test section. That will tell you why we need so many optical panels. It's non-corrosive because we want to deal with the salty water, so everything is made up of plastic or fiberglass. It's stirred and energetic. Basically, we have to use a lot of jets in order to create a turbulence, and this is basically the facility we have. In the facility, the first feature is the mean flow. We had to make sure the mean flow is going down and at a speed that balanced with the rising velocity of bubbles. And the reason for that is because for those bubbles that rise from the bottom, we want to keep them in the test section as long as we can, so we can measure their interaction with the surrounding turbulence. Otherwise, we just go through using their rising velocity, so we won't be able to take a lot of statistics. So that's the first design idea. I'm not sure if you can see it here. Here, only turn on the mean flow. The bubbles want to rise up, but they couldn't because of the downward flow is actually keeping them in the test section. So this is stalling their rising motion. So that was successful. But the problem here is just the mean flow alone is not enough to kick enough turbulence with a high energy dissipation rate. So in addition to the mean flow, we need to independently control the turbulence level inside this facility. So the way we did it is basically we take out the test section here, and we put a jet array on top of the test section. And in this jet array, we spent a lot of time to work on the jet array because we had to put a lot of pressure through the jet array in order to shoot high-speed jets through those nozzles. Here you can have the square opening on the right, and you also have a lot of the circular opening that's actually a nozzle for jets. So the square opening is basically allow the mean flow to pass, and the circular opening is basically to shoot a lot of high-speed jets. This is actually a very fun exercise because that was the first time we designed something, trying to fabricate it using additive manufacturing. We tried a lot of different material. Every material we tried basically exploded in the end after we put a lot of pressure on. This is the only structure that survived using the sinter bead idea. It actually worked pretty well. So the internal structure looks like this here. So you have a lot of internal channels that go direct the jet from side injection to the coaxially with the mean flow. So the mean flow basically comes through the square openings, and the jets basically coming from side and shoot coaxially with the mean flow. And the jet velocity can go up to 15 meters per second. This is basically the limit that we can go without cavitating the flow. So this is basically allows us to inject a lot of energy, turbulent energy, into the test section. At the bottom, we have the capillary island here. And the bubbles typically are rising to roughly the center area. We have a lot of cameras surrounding those this area. So this is basically bubbles coming in and interact with eddies. At the same time, we have 6 high-speed cameras surrounding the entire test section. And each camera can capture the flow at a 5,000 frames per second with 1 megapixel resolution. And I think there's a bit of feedback here. I'm gonna try to stay away from the location there. And we have LED panels for each camera just to see the backlighting, and so we can see exactly what's inside of this test section. And this is basically one of the raw video for the bubbles. And question for you guys, do you know which one is the vertical direction? It's hard to tell, right? And the reason for that is because the turbulence is actually very, very strong and intense. By the way, I intentionally rotated this 90 degrees. So if you think this is a vertical direction, that's not the case. This is a vertical direction. So this is trying to tell you that the turbulence is so intense that it can preferentially deform the bubble isotropically around all kinds of different directions instead of preferentially along the vertical direction where the buoyancy is. So this is really a test that the turbulence is actually driving the deformation, not the buoyancy. Okay, and in this case, you can also see a lot of background small tracer particles. Those are actually the tracer particles put in to see the surrounding turbulent flow. This is a raw images of both bubbles and the surrounding tracer particles. And typically what we do is we separate the bubble images and the particle images. I'm going to zoom into the small area around this bubble, and you can really see a lot of tracer particles. This high concentration tracer particle was a bit challenging to deal with in the very beginning because we really wanted to do three-dimensional particle tracking. So eventually we spent actually 2 years of our time trying to get the particle trajectory mapped out from 6 cameras. And this is one of the results we got. So basically we designed this open source shake the box method. It's parallelized, can be run on HPC. So we actually take a lot of resources from our computational colleagues. And I don't think they're all very happy with our exercises, but that's what we do. We take their resources and try to speed up the calculation. Not that sounds wrong, but anyway. Essentially we can get very high concentration of particles trajectories. And from that we can calculate the turbulence statistics. So this is basically the turbulence characteristics. So essentially what we have here is I mentioned this as a classical common graph theory about the hydrodynamic turbulence. You can see that there's a spectrum here that should the second order structure function should follow the 2/3 power law. And this is very easy to calculate because you have many pairs of particles. You can just pick 2 and with R separation, then you can calculate the structure function. Essentially, this is experimental data. And there's a range of scales. You have this 2/3 power law scaling that indicates existence of the inertial range in turbulence. So this is basically confirming the 1941 theory of single phase turbulence is correct, right? So the next thing to do, actually, people already know this for a long time. This is nothing new here. Next thing we can do is from this inertial range scaling, because this is related to the energy dissipation rate here, we can also get the energy dissipation rate mapped out. So this is basically the table I showed you before. This is the second column here is basically the energy dissipation rate got from different facilities before. And now we basically, from the structure function, we can actually get our own energy dissipation rate. In comparison with other energy dissipation rate, you can see ours are a lot higher, except for this one. This one is actually getting very close. But also our facility specified the criterion we sort of proposed before that in order to get to the turbulence stress is dominant the deformation, we need to make sure our energy dissipation rate is larger than 0.1. And we have satisfied that. And by the way, we're rebuilding this facility or improving the system a lot. So in this case, we can actually get into almost 1 instead of 0.1. Anyway, so that's basically showing you that we can build a facility that can reach the proposed energy dissipation rate. We can also measure a high concentration of tracer particles in there. And the last thing we need to do is basically trying to get the shape of the deforming bubbles. This is actually a very interesting exercise because in computer vision community, computer science people know this for ages, and the way to reconstruct let's say, if you're an actor or actress, you enter a studio, you want to map out the entire three-dimensional motion of your body. You basically walk into a room covered with like hundreds of cameras, and you can just act, and then afterwards it automatically generates a three-dimensional geometry. We basically use the same idea. The only difference here is typically you would require hundreds of cameras, but we're using high-speed cameras. Each camera costs maybe 10K, let's say. And hundreds of that is, it's impossible for me. Maybe it's possible from some colleagues in this department, but that wasn't possible for me. So let's say I can only afford 6. By the way, the way that I get a 6 is because I collaborate with other people that's richer than me, so they can get 6 cameras. So right now, let's say you have 6 cameras here. Okay, so this is actually a direct numerical simulation I got from our department chair. Actually, Greta, who's actually the faculty member in this department before. Anyway, so he gave me this very nice simulation data set. I use that to reconstruct, and I compared that with a direct numerical simulation. So in this case, I'm using DNA to validate experiments method. Anyway, that's sort of against everything I believe in, but it is what it is. So this is basically a comparison between the reconstructed geometry versus a DNS case. You see that pretty close to each other. That reassure us, with the 6 cameras, you can get a pretty good reconstruction of deformable particles. All right. So up to this point, I told you the key hypothesis I'm targeting. I'm telling you that we need to get an energy dissipation rate larger than 0.1. And we built a system that successfully achieved this designed value. So we have a strong energy dissipation rate. We can use this to generate the deformation that's turbulence dominated. And then we can also measure the carrier phase using high concentration tracers and in-house shake the box code. We can also reconstruct the 3D geometry of deformable bubbles. So we have everything we need theoretically. So now we can do some physics in this problem. First of all, I want to show you some fancy movies. This is basically a case of the tracer particles or tracer trajectories surrounding deformable bubbles, and the bubble is actually deforming all the way to the breakout point. And you can see that we can get the three-dimensional geometry of the bubbles and surrounding tracer particles are all measured successfully. So that's good. And we also said we want to understand the deformation mechanism and compare that with a classical Kolmogorov-Hintz theory. So here's we're going to do that. On the left, you saw the same video I just showed you before. And in this case, if I remove a lot of the small scale, the chaotic motion, the motion, the large scale motion looks like this. You sort of have a flow that comes compressing the bubble along this direction and then stretch it along the horizontal direction. So basically, this is the white arrow here is basically showing you the large scale motion, or the motion actually at a bubble scale. And the red arrow here shows you the most compressive direction. That's called E3. This is basically the eigenvector of one of the strain rate tensor. And E1 here is basically the maximum eigenvector, or the eigenvector with maximum eigenvalue of the rate of strain tensor. This is basically the red arrow basically compressing the bubble, and the cyan arrow is basically stretching the bubble. So this makes sense. This is actually consistent with Kolmogorov-Hintz theory. The bubble is being deformed by this kind of a stretching motion at the bubble size, all right? Because this strain rate tensor is essentially at a bubble scale. In addition to that, we also saw a lot of cases the bubble is being deformed and broken by this kind of slapping motion. Basically, the bubble gets slapped by the turbulent flow along one direction, and the bubble tried to rise up along this direction, but eventually got broken around that slapping direction. So that kind of slapping motion, what I call that is basically the due to the velocity discrepancy between the two phases. Essentially, bubble wants to rise up to this direction, but the incoming flow is actually coming from the horizontal direction. If you take the difference between the two velocity vectors, this is basically slip velocity direction. And the slip velocity direction turns out to be almost exactly aligned with this minor axis of the bubble, indicating that the slip velocity is actually compressing the bubble. So this is sort of the slip velocity is sort of a newish. People already know that in the spray community, atomization community, but for the bubble community, especially in homogeneous isotropic turbulence, there's no mean shear in the problem. So the slip velocity is actually due to the random motion of the surrounding eddies, and also because the bubble cannot really follow the surrounding eddies perfectly due to added mass force. So that's sort of the interesting new insight. The way I'm picturing this problem together is by using this very simple Taylor expansion to understand different kind of a contribution to the deformation problem. So exactly what I'm showing here is it's nothing but a Taylor expansion. Okay, don't get it too complicated here. So essentially, for each bubble, all right, I'm going to find a lot of tracer particles around the bubble. So the tracer particle velocity, I call it UIP. All right, P basically stands for particle, I basically stands for the indices of those tracer particles. If I do a Taylor expansion of the surrounding tracer particles into different sort of terms, the first term I got is basically the uniform flow part. Essentially, that's a component where all the tracer particles basically moving in the same direction. And that is that's contributed by the eddies larger than the bubble size, if you will. Essentially, if the bubble is this big and you have a gigantic eddy like this, and for the bubble itself, it looks like there's just a uniform flow. Make sense? So that's sort of a large eddy contribution. And this is contribution from eddy of the bubble size, because that's basically the linear gradient around the bubbles. And that's very similar to the Kolmogorov-Hintz hypothesis, where you basically take two velocity and take the difference between them. That's basically represent the turbulence stresses. So essentially, I want to mark that the Kolmogorov-Hintz assumption is focused primarily on the flow velocity at the bubble scale. So this is basically what they focused on. But they essentially ignore the contribution from either the large ones or the small ones. The small ones is basically the higher order. So So this is A here is the velocity gradient, and H here is velocity Haitian. So that's the gradient of the velocity gradient. So that's actually much smaller scales compared with the bubble size. So I'm representing that with a lot of small arrows to show that they are small eddies. So essentially you have bubble size eddies versus larger eddies and the smaller eddies. Okay, and in this case, we just showed that the contribution by the larger eddies. And the reason I said that is because in the slapping motion I mentioned before, it's due to the flow that's relatively uniform at the bubble scale. And the flow that's relatively uniform at the bubble scale is basically larger eddies. So in this case, bubbles do not follow the surrounding flow, and that causing the slip velocity. The slip velocity is essentially the bubble velocity minus the average velocity at the bubble scale. So that's represent the larger scale contribution, large scale eddy contribution. So essentially, what I'm trying to saying here is, in addition to the Kolmogorov-Hines assumption, maybe the slip velocity is also significant or important for the deformation for bubbles. Let's just check if that's the case. So I want to focus on the large scale motion, and here I'm using DE, and DE basically indicating the eddy scale. DE is an eddy scale and D is a bubble scale. So we're trying to focus on a large scale, the eddy with a size larger than bubble size. All right, how do we confirm the contribution of the deformation induced by the large eddies? So first of all, we're still going back to this framework. This is a straining flow around the bubbles. I'm assuming that's a flow of the bubble scale, right? And if you put the straining flow here, if you imagine the bubble is basically compressed by the eigenvector of the compressive direction, so we basically call the eigenvalue of that direction λ3, you can actually get a Webb number for this particular deformation case. So instead of U, we basically replace U with λ3 multiplied by D. So that's basically the velocity gradient across the bubble diameter. So that we are still assume that this eddy of the bubble size. That's why we're using capital D here. And on the picture here, I'm showing the Webb number distribution. So this is a Webb number around individual deforming bubbles, and we're trying to check the probability density function of this Webb number. You can see that it follows a roughly log normal distribution. So this is actually quite consistent with the Kolmogorov's series for single phase turbulence. The other case is actually different. This is slip velocity because due to the mismatch between the two faces, the velocity mismatch between two faces, and instead of putting in something related to capital D, we keep directly putting the U slip. And this is basically has no scale. This is or alternatively, I should say, this is basically related to the scale larger than the bubble. Okay, and you can see that it follows a very different distribution, so indicating they have a very different mechanism behind these two deformation. And we can explain that. So this is a log normal distribution. We can actually fit a log normal curve to the Webb number distribution here. For the other one, it's a bit more complicated. So we have to use this called a stretched exponential function for the slip velocity. And after you putting that into the Webb number definition, you can get this blue line, which sort of agree with the symbols pretty well. So that's basically indicating both the large eddies and the eddies of the bubble size contributing to the deformation. One thing I want to point out is we should only pay attention to the Webb number that's larger than 1 because that's basically contributing to the bubble deformation. Smaller than 1, that doesn't contribute much. So you can look at that. The right tail of these two symbols actually agree with each other pretty well. So that was actually a little bit disappointing to me because that's basically indicating even they have a different mechanism of deforming the bubble. I couldn't really separate them simply because the PDF is too close to each other. So how do we do that? Because the magnitude of the Webb number doesn't seem to make a difference. In that case, I need to try to change something to the orientation. So here what we did is we said that all these angles, all these vectors like a λ3, E3, or the minor and the major axis of the bubble, R1, R3, they are vectors. If you have two vectors, you can always compare the orientation. So in addition to, this is basically Kolmogorov-Hines framework. This is basically a large eddy contribution. And you can see that the slip velocity is a vector and R1, R3 also vectors. So we can compare the orientation. The way you compare the orientation between two vectors is basically take the dot product between the two. And the dot product, if it's very close to 1, that basically means they're aligned. If the dot product is close to 0, that means they're perpendicular to each other. So if you look at this PDF here, it shows that the R3, which is minor axis of the bubble, aligns with preferentially with E3. So this is confirms the Hopkins idea, which is the bubble is being compressed instead of being stretched, compressed by the velocity gradient tensor along the sort of E3 direction. But if you look at the slit velocity alignment with R3, you can realize that it's actually have a better alignment because you look at the magnitude here, this is only at 1.4, at 1.5, this is almost at 4, which means the minor axis of the bubble aligns better with the slit velocity than along with the velocity gradient tensor. That indicates that for bubble deformation, the dominant case is actually the slit velocity instead of the velocity gradient at the bubble size. So that's basically the key message I'm trying to talk about. This is the first missing piece in the Hopkins framework. Actually, Hopkins and Hins probably knew that already because they use most of the droplets of the density matched. But in our case, we're talking about bubbles, and that is density mismatch. So that's why we have large scale motion. So the first missing piece, when we talk about the bubble breakup or fragmentation in turbulence, you had to account for the large scale motion. And large scale motion is basically the eddies with length scale dE larger than the bubble scale. Okay, so that's the first missing piece. The second missing piece is actually more interesting to some degree. This is about the fragmentation in intense turbulence. When we have the fragmentation, I always have this problem since day one. How do I disentangle eddies of different sizes? I think as a turbulence guy, this is a sort of a holy grail of a problem is, how do we really get it? How do we define eddies here? So if you go back to this Taylor expansion, so I already make a case that, all right, so this is the first term here, maybe it's for large scale motion, right? It's large eddies. Second term here is basically eddy of the bubble size because this is a linear gradient across the bubble of certain size. So this is really the flow around the bubble size. And the third term here is a small scale contribution. If we're clear on that, that's great. But now the question is, I really want to know the contribution, but so far we've been working primarily on the bubble scale and large scale. What about the small scale? The small scale is kind of hard to deal with. The reason it's hard to deal with is because in order to get the small scale contribution, you had to take your measurements, basically you have a tracer velocity, and subtract the mean, and then subtract the linear gradient. And what's left is a high order term. Does that make sense to everyone? So the problem here is the noise also goes up as you're subtracting more terms. You're subtracting the leading order, second order, and whatever left is basically mixture between the signal and the noise. So signal to noise ratio for a small eddy contribution is terrible. So as an experimentalist, how do we deal with this problem? Whenever you have a problem that you have to deal with a lot of small eddies contribution, you have two ways. The first way is control inputs. Essentially, if you can control inputs that kill the first two leading orders and only leave with the small eddy contribution, that's a successful experiment. Alternatively, you can improve your diagnostic system that you can really improve the resolution of your measurement so you can resolve the small scale motion. All right, we tried this first. We tried the diagnostic methods. The reason we spent so much time on this diagnostic method, we were trying to improve the resolution of velocity and spatial resolution in order to get rid of the large scale motion and focus on small scale. And that failed miserably. And also we tried the first one, and we realized that it's very hard to use a fully developed turbulence to do this problem because the fully developed turbulence have all scales. You cannot get rid of the first two leading orders. So that really proposed a very important challenge to our experimental effort is how do we get rid of the first two leading orders? And the way we did that is use the so-called vortex ring collision. And this is actually a fairly simple experiment that was done initially by 2 undergrad students. So this is actually, if you haven't seen this kind of YouTube video before, you can find it easily. Basically, you have 2 vortex rings. You push them against each other, then they collide. And after that, you're going to generate a turbulent cloud. So I'm going to play this here. They collide, then they expand, then you shoot out a lot of the turbulent cloud. So actually, McKeown in Harvard, they actually did a lot of very detailed measurements and direct numerical simulation. I actually got data from them. I want to credit my friend Rodolfo, and he did a direct numerical simulation. You really have a ring. This is only one ring, right? Instead of two. You have rings so that can become unstable and eventually generate this turbulent cloud. So this is a fantastic study to understand the fundamentals of the turbulence cascade. When I saw this, I feel like, wait a sec, this is actually a nice way to separate large scale from small scales. And you have two stages. In the very beginning of the stage, you have this clean vortex line. It has only one length scale here. This is basically my large scale. And afterwards, you have this cloud. The length scale of all these eddies here are much smaller than the length scale here. So you either have large scale contribution or small scale contribution. Okay, I call it magic knife that can separate the scales of eddies. So we decide to put a bubble in here. So in the very beginning, the bubble will interact with large eddy alone without a small eddy contribution. And afterwards, this bubble will break up into two daughter bubbles. And daughter bubbles are going to actually interacting with the smaller eddies. Okay, so which one is actually can have a more violent breakup? You can try to picture in your mind and give me an answer if you want. So this is basically the hypothesis of the experimental apparatus we proposed. And over the summer, basically two undergrad students, they basically built this facility. And this facility is just the two pistons driving the two cylinders and be driven in the cylinder and push the fluid out. And then when the fluid is being pushed out, it generates two beautiful vortex rings. And then at the bottom of the tank, we have a syringe pump that will inject a bubble. And the bubble will actually interact with the vortex ring. We have to synchronize everything really, really well because it's very important the bubble is rising at the exact time when the two vortex rings colliding with each other. In this case, you can actually see this very beautiful results. And we did the same thing like what we did before. We have all the high-speed cameras surrounding this facility. We can measure the bubbles and surrounding flows exactly like what we did before. All right. So similar to what we had talked about before, we would try to use a second-order structure function to determine the energy of different eddies. And this dash box here is basically my V volume. And in the very beginning, you have only one length scale here. So you can see that most of the energy, because S2 is basically has a scale of energy, you can see that most of the kinetic energy is dominated by the large vortex, which is here. All right. So then, at a later time, you have this turbulent cloud. And I do the same calculation of the structure function, and you realize that the structure function becomes this red curve. And you have a two-thirds scaling, which means that there's an inertial range here. This structure function actually stays unchanged for almost one integral time scale. And during this time, we're going to try to look into the bubble breakup. All right, so that's basically the background flow. And now I'm going to put bubbles in there. When I put bubbles in there, I'm going to try to show you the web number distribution. So I'm going to color code everything. So the magenta ring here is showing you basically the one large vortex. I call it primary. This bubble breakup here, I call it primary breakup. And the bluish color here shows you the secondary, which is basically turbulent cloud. The bubble breakup in this case, I call it secondary breakup. If you use the traditional definition of web number, by the way, these two web numbers are defined based on the bubble size of eddy, okay? And what you realize that is this one has larger web number. So the PDF of the web number for the primary breakup is larger, okay? In the common ground Higgs framework, it essentially indicates larger web number means larger probability of breakup and more violent breakup, okay? Because the stress from the surrounding flow is higher and much larger than the relaxation force due to the surface tension, okay? So the primary cases have larger web numbers. So the common ground Higgs framework essentially suggests that should be more violent and faster. Let's see if that's the case. Here I'm gonna show you two movies. I'm gonna play at exactly the same time so you can count how much time it takes for the primary breakup and the secondary breakup. You can clearly see that primary breakup is large, the primary bubble is larger, right? If you look at the web number, larger bubble is actually easier to break up. A secondary bubble is actually smaller. Let me remind you, this is a larger web number, okay? So if I start to play, what you realize that is a secondary breakup, which with a smaller web number, breaks a lot faster and more violently than the primary breakup. As a reminder, I'm going to put a text here. The primary breakup has larger web number, slow breakup. And the secondary breakup is actually smaller web number, but the breakup is more violent and rapid. Okay. So this is actually opposite to what common graphing hints predicted before. So that's why I'm trying to summarize here. We built this vortex ring bubble collision experiment. And we found a second missing piece, which is a smaller scale flow when the eddy size dE is smaller than d, and is actually crucial to the breakup. And the reason we can generate the eddy size smaller than d is because of this the vortex ring breakdown, and we can generate a lot of fine eddies in the secondary breakup. And it turns out the secondary breakup is actually dominated by those small eddies. But that's sort of phenomenological. I want to show this more conclusively in a model. So that's basically what we did. We tried to generate a model. So in this model, the difference here is traditionally we only focus on the web number. And the web number essentially is arguing about the stress ratio. Is it saying that local stress induced by the turbulence is stronger than the relaxation force? But here, instead of saying the scale is related to the bubble size, I'm picturing this, you have a bubble that's being indented by an eddy of size dE. And essentially the criteria of breakup, instead of saying that in global deformation, I'm talking about the local deformation. The first criteria I mentioned is local stress generated by the eddy has to be larger than the surface tension locally. The second criteria is this is actually more important. This is probably a revision to the Combs-Hinds original proposal framework. This is an important piece. This is basically talking about the interaction time. The argument I'm trying to make here is no matter how long the eddies interact with bubble, it has to happen so fast before the bubble actually relaxes back to sphere. So this is a time criteria. When you put this time criteria on the same figure, you realize that the stress criteria is actually going down as a function of dE. So when the dE approaching the bubble size, when the eddy size approaching the bubble size, the stress criteria goes down, but the time scale actually goes up. So the only way you can break the bubble is for the eddy velocity to larger than this envelope here. So this region for the breakup, and the region below that is actually no breakup. So essentially, this simple model, basically two different dimensionless number, give you the criteria for the eddy velocity. The eddy velocity has to be larger than this envelope in order to break up. Once you have this, it becomes actually quite easy to get other quantities. For example, we know that the turbulence has this eddy velocity distribution based on the energy dissipation rate distribution. This is actually the log-normal distribution based on the Kolmogorov 1962 work. And you can also derive this equation from multifraction model. I'm not going to get into the details. All you need to know is this equation is a given to talk about the distribution of energy dissipation rate for the eddy. And then from that equation, you can get the equation for the probability for the eddy velocity. And all we need to do is asking how many of this eddy velocity is above the limit we have. So we integrate this probability from the minimum eddy velocity that can break a bubble to infinity to get this probability of one large bubble broken by eddy of a smaller size. So you can see that this is a basic, I'm trying to guide you through this figure. The horizontal axis is eddy, the scale ratio between the eddy size to the bubble size. If it's at this scale, if it's peaked at this scale, that means the eddy of the bubble size has a largest contribution to the bubble breakup. But yet the peak is actually somewhere smaller than 1, that indicating the small eddy is actually more important for fragmentation. This is considering a collision between one bubble and one eddy. And here we can consider the eddy sort of a number density because small eddies are more abundant in the turbulence. And you can see that it's basically follow the same shape, but what's important here is the peak is still smaller than 1, that indicating the sub-bubble scale eddy is very, very important. Another important thing is when the bubble size becomes larger, this curve becomes flatter, as because the contribution by smaller eddies is actually growing when the bubble size is actually larger. So this is a completely opposite to what the Kolmogorov-Hinds hypothesized. They're saying the eddy size that's similar to the bubble size actually have the highest contribution, but in our model, we're suggesting that the subbubble eddy has more contribution. All right. So this is a key hypothesis for our framework. The subbubble scale eddies are more important. And then we can compare that with our experiments. So this is our experimental data. The data has been noisy because in the vortex ring breakup case, you don't have a lot of statistics. So this is a basic breakup time as a function of the bubble size. If we use our model, this is a model prediction. I think it agrees pretty well with the experimental results. By the way, there's no fitting parameter in the model. So this is just a direct prediction of the breakup time. We're not really happy with this. So what we decided to do is trying to check if there are other experimental data that we can use. So this is another data by Vodrowska back in 2018. This is similar to our facility. And they have a bubble injection. They have a lot of jets coming down, interacting with the bubbles. And they can get a pretty wide range of energy dissipation rate because they don't care about the homogeneous isotropic. They actually capture the bubble broken directly by the head of the jet. So they can actually get to very, very large energy dissipation rate. And the vertical axis is the breakup frequency. If you use Hopkins framework, this is the model prediction. You can see that not only it doesn't capture the magnitude of the breakup frequency, it's also missed the scaling because you can see that experimental data is growing faster as a function of energy dissipation rate compared with the model predicts. So in our case, we have a prediction of the 0.2 energy dissipation rate 0.2. This is basically the same figure you saw before. The 0.2 is roughly here in this diagram. So this is basically the model prediction. And when we increase energy dissipation rate, you realize that the peaks of all the curves shifted to the left. And let me remind you that the left of this curve is basically smaller eddies. Essentially, what that indicates is for larger energy dissipation rate at the 5.0 meters squared per cubic second, the contribution of small eddies is actually growing, and the importance of that is actually growing and growing for all bubble sizes considered. And when we take everything into account, this is basically 5.0 is roughly here. We can see that the reason the experimental data grows faster than the model predicts is because it misses this very important mechanism that smaller eddies contributions are become more significant at a large energy dissipation rate. Since smaller eddies have a higher frequency, so that's why the breakup frequency becomes higher. If we take that into account and we put this model together, and those are the model prediction, you can see that agrees pretty well with this particular experimental data set that we used. And that sort of indicates that the new model, which includes the subbubble scale contribution and the time scale, is actually becomes more successful than the classical framework. All right. I think I used all my time here. As a summary, I asked a very simple question in the very beginning of my talk. Is the key hypothesis in the Hopkins framework correct? And when I say the key hypothesis, I basically Hopkins assume that the bubbles are preferentially fragmented by eddies of the same size. And the answer to the question is the assumption that only one length scales matters is incorrect. Okay, and we have direct evidence to disprove that. And so the eddy size is actually quite important. When you follow this logic, you will realize that just the Webb number is not sufficient. One needs more than just the Webb number to describe fragmentation. Actually, the ratio of time scale is equally, if not more important. Finally, I want to clarify a mystery here. In the community of fragmentation, people typically connect large Webb number basically indicates large deformation. Large deformation basically implies fragmentation. I want to say that that's definitely not correct. And based on this framework, what we have found out is the deformation is typically driven by large scale eddies. Essentially, deformation are driven by eddies that have more energy. So in this case, the slip velocity are driven by larger eddies and the eddies of the bubble size all contribute to deformation. But deformation does not mean fragmentation. Fragmentation is actually requires something that can hit the bubble, release all the energy within a short period of time. So in that case, actually large eddies becomes less efficient compared with small eddies because their lifetime is much shorter, and they can actually cause local deformation that can be so severe that can break the bubble into two parts directly without actually elongate them into a large aspiration. With that, I want to thank everybody for your attention and I welcome any questions. Thank you.
Folks in the virtual or physical audience, I see Phil Schultz has some questions. And maybe because you have the mic, you can just repeat the question.
Okay, I can read it here.
Yeah, why don't you read it? There's two of them.
All right, so the first question is, why does it look like there are sharp ridges on the surface of the bubble? The connected lines of low curvature radius, is this a result of reconstruction with just 6 hammers, or are the ridges physical? That's a very good question. And sometimes the ridges are definitely not physical and due to the reconstruction because we only have 6 hammers. And occasionally, if you have something that hide in the away from all 6 hammers, you will end up with ridges that's non-physical. And we calculate this kind of reconstruction fidelity. We have about a 20% of the error sometimes, and that's just due to those kind of physical materials after the reconstruction. But occasionally, those are actually real. When I say real, I basically can justify that ridge sort of appears in several consecutive frames, and I can actually see that features on one of the cameras. So then I can call it real. But it's very hard to draw a line to say which one is real, which one is not, because there is an inherent reconstruction problem due to the limited number of cameras. So that's the first question. The second question here is, how is the slip velocity related to the presence of surfactants? To what degree do you worry or avoid for surfactants in your experiments? This is my recurring nightmare about surfactant. I hate surfactant and I don't want surfactant. I've tried everything I can do to get rid of surfactant. But I know it's there. The reason I know it's there is because you cannot get rid of surfactant. That's a fact. So in reality, what we do is we try to use deionized water and put it into the tunnel and try as much as we can to filter every some kind of contaminant in the tunnel. But then afterwards, I put the tracer particles in there. And sort of the tracer particle definitely has some surfactant in there. So I cannot really guarantee you that there's no surfactant. Actually, we did one experiment to test that. So we turn off everything and we put the tracer particles in there and we let the bubble rise up. And that's actually a classical test to see how much contamination you have in the system. Because if you really have a strong contamination, the bubble rise velocity will deviate from that in the clean interface. So we saw the deviation, we know it's contaminated. So that's, I can conclusively say that that is a problem. How is the slip velocity related to the presence of surfactants? I think that's actually, the presence of surfactant probably doesn't change the slip velocity too much. If you're talking about the boundary condition, that is definitely changed because the one is a slip boundary condition, the other one is no slip boundary condition. But the slip velocity, the magnitude of the slip velocity is driven by the mismatch of velocity and also the added mass force for bubbles and the finite size effect. And none of that is actually affected by the surfactant. Not sure if that's clear. If you have any follow-up questions, feel free to unmute yourself, I guess. And then the third question I have here, by the way, before I get into the third question, any questions from the audience in person? I feel like you guys made your effort here. Maybe I should prioritize you guys first. Any questions? The nice thing about in-person presentation is you guys cannot hide from me. I'm staring at you right now.
I think going back to this slip velocity. Depending on what scale you look at, you'll have no slip. This idea of slip only exists because of bigger, right? It's E over a larger scale. I don't know if Professor Schultz was thinking slip velocity was at the surface.
Right.
It's very different than the slip based on the course.
Exactly. Yeah. That's why I was hesitating to suggest if the slip velocity he meant is like a boundary condition thing, or it's more like a large scale for the entire bubble. But for surfactant, it definitely changed the boundary condition. So it becomes no slip instead of slip.
Yeah. So the presence of slip velocity, Reynolds average framework, would be turbulence. It has a production of turbulence in the presence of bubbles, right? Bubble is turbulence. And there's, as you know, a number of papers recently looking doing DNS. And the drag force at times the slip velocity actually works that produces turbulence. So I wonder, even focusing on bubble morphology, bubble dynamics, have you looked at its effect back on the fluid dynamics? That would be shed a lot of light on those, others.
Right. Just for the audience on Zoom, I think Jesse is basically asking questions about if we consider bubbles are completely passive to the surrounding flow, or they actually actively injecting energy to the surrounding turbulence. And the answer to that is, in this framework, we didn't consider the bubble-induced turbulence, and for a number of reasons. The most important reason is because in this particular case, we assume the concentration is fairly low. The bubble encounter a bunch of turbulence, and that the modulated turbulence is basically back away from the bubble as soon as that being injected to the surrounding flow.
But anytime you have finite slip, it has to be.
I'm not denying that. So there is definitely some effect to the surrounding flow. What I'm saying is, at a second or some time later, that flow has already been affected away, and because the concentration is fairly dilute, and that sort of affected flow sort of just disappear from my control bond. So that's sort of the assumption or hypothesis I made in this framework.
Do you have any plans on looking at that higher concentration regime?
Yeah, we're doing actually, as we speak, new experiments. We're trying to inject a lot of bubbles and then measure the downstream flow and see how much. So we can talk more about that, because I have a hypothesis that deformation could change how the two phases couple with each other. So in a lot of cases, people have studied before the bubble-induced turbulence focusing on the bubble deformation primarily driven by buoyancy, and there's no sort of a pre-existing turbulence. And we're trying to see how the pre-existing turbulence affect the deformation and how the deformation affect the surrounding turbulence. Yeah. Any other questions from the audience? Yes, please. I'm sorry, can I hear? Bubble collapse? No, because those are gas bubbles, not cavitation bubbles. So that's why we don't have a too significant change of pressure that could cause the bubble to completely collapse. The pressure we're talking about here is barely sufficient. And one thing I want to make it very clear, we're talking about dynamic pressure, not the static pressure here. So the dynamic pressure is basically deform the bubble, but when you're compressing this way, it has to be stretched or extended through a different direction. The only way you can collapse it completely is by changing the static pressure. For gas bubble, it's very hard because when I talk about gas bubble, it's now made of vapor. So the gas is insoluble in water. So you need a lot of pressure in order to completely collapse that. And also we're talking about millimeter, not a micron size. For micron size, you probably can do that, but for millimeter, it's very hard. All right, thank you. Any other questions? Go ahead.
So is there any connection between this and the bubble size speeding off?
That's a question I always try to ask myself. The key is, as I mentioned to you yesterday, the bubble size spectrum is fairly robust, independent of how you. You only need one assumption, and that assumption is very, very strong. And unfortunately, I haven't seen any ways that this framework can actually change that skating law. So that's the short answer, and the longer answer I can give you after the talk. Yeah. Any other questions? All right. You guys are not avoiding eye contact, so that's a good sign. You understand everything I said. Okay. So the third question on Zoom is, are there any universal laws in the shape of the fragmented bubbles for given some eddies? The shape of deformed bubbles may be able to be decomposed by some basis, for example, spherical harmonics. And I was curious if there exists a relation between eddy size and some length scale in the decomposed bubble shape. That's actually very insightful question, I think. We tried the spherical harmonics, and other groups also tried that before. The problem with the spherical harmonics is typically assume the deformation is fairly small, very small amplitude, because the spherical harmonics essentially assume that you have a fairly the entire bubble geometry is still relatively spherical. But when you're putting that in turbulence, actually you realize that the entire geometry is not even axisymmetrical anymore. So when you try to decompose that into the spherical harmonics, it becomes actually quite difficult, if even possible. So we tried that, but it didn't really work that well. So that's why we were thinking about other ways to do it. There are other sort of more advanced ways to decompose the geometry. And certainly that's probably going to be useful in the future, because right now we're trying to do the machine learning, basically input all the interface points from the bubble reconstruction and surrounding flows, and see if that can tell us a little bit more about the interaction between the two faces. All right, I think I answered all the questions on the Zoom. Any other questions from the audience?
I think with the time.
Thank you so much.
All right, great.